Welcome to the deep dive. We're here to unpack complex stuff and hopefully make it, well, fascinating and easy to grasp.
Yeah, absolutely.
Think about it for a second. The food you eat, medicines you might take, even just the air around us, it's all fundamentally chemistry. Amazing chemical structures.
It really is. And intricate ones, too.
So today we're doing a deep dive looking into a key chapter from Timberlake's chemistry, an introduction to general organic and biological chemistry.
Right. A foundational text.
Our mission, to get our heads around four really important organic functional groups: carboxylic acids, esters, amines, and amines. They pop up everywhere.
They really do. And what's so interesting is how these concepts, which might seem a bit abstract, have such direct practical relevance, especially in health and life sciences.
Like how?
Well, the source material talks about someone named Lance. He's an environmental health practitioner. His job involves monitoring pollution, testing soil, testing water samples. Picture him out on a ranch, maybe testing for pesticides or even pharmaceuticals used on animals, like fendibendazole for sheep parasites.
So he's like a chemical detective then, trying to figure out what specific molecules are out there in the environment.
Exactly. That's a great way to put it. And to do that job well, he needs to understand the chemical structures, the functional groups, things like esters, amides, amines, which we're covering, and also things like aromatic rings, those stable carbon rings.
Okay.
Knowing what these molecules look like, how they're built, is absolutely vital for him to identify pollutants and, protect public health. It really grounds why this stuff matters.
That makes total sense. You need the building blocks to understand the bigger picture. Okay, let's dive in. First group, carboxylic acids. I feel like I know these. They're the sour ones.
You got it. They're everywhere. Carboxylic acids are technically weak acids, but yeah, they're known for that sour or tart taste.
What makes them tick, chemically speaking?
It's all about the carboxyl group. That's their signature feature. It's a combination. You've got a carbonyl group that's a carbon double bonded to an oxygen,
Okay.
attached directly to a hydroxyl group, an OH group. That specific C double bond O, single bond OH arrangement. That's the key.
Got it. Two bits stuck together, and you said they're common?
Oh, absolutely.
Right.
Vinegar, that's basically just acetic acid mixed with water.
Right.
Or when you bite into a lemon or grapefruit, that sharp sourness, citric acid. And less pleasantly, if you've ever been stung by a bee or, a red ant, that sting comes from formic acid.
Ouch. Okay, yeah. Very memorable example. So how do chemists actually name these things systematically?
Well, the official IUPAC way is pretty logical. You find the longest carbon chain, including the carboxyl group, take the alkane name, drop the final E, and add oleic acid. So methane becomes methanoic acid, ethane becomes ethanoic acid.
Simple enough.
But honestly, lots of them have common names we use more often, and those names usually hint at where they were first found, like form, in formic acid comes from formica, Latin for ant.
No way.
Yeah, and acid in acetic acid is from acetum, Latin for vinegar. Butyr in butyric acid. That relates to butter specifically, rancid butter smell. Ugh.
Ha. Okay, names tell stories. Love that. But what about their properties? What makes them behave the way they do?
Well, that carboxyl group with its double bonded oxygen and the OH group makes them very polar.
Right. Polar means they mix well with water.
Exactly, especially the smaller ones, say up to 5 carbons. They form strong hydrogen bonds with water molecules, similar to alcohols. That's why they dissolve so easily in water, which is super important for biological systems.
Makes sense. Our bodies are mostly water, and they're weak acids, you said.
That's right, weak acids. So in water, only a little bit of them actually breaks apart or dissociates into a negatively charged carboxylate ion and a hydronium ion, H3O+.
Only a bit.
Only a bit. But, and this is key, because they are acids, even weak ones, they react completely with strong bases. Think sodium hydroxide, potassium hydroxide.
Yeah.
That reaction neutralizes them.
Neutralization. So they form a salt and water.
Precisely. You get a carboxylate, salt, and water.
And these salts, they're not just stuck in the lab, right? Do we use them?
We absolutely do. This is the so what moment. These carboxylate salts are huge as preservatives and even flavor enhancers. You know sodium propanoate. It's often in bread and cheese to stop mold.
Ah, okay.
Sodium benzoate does a similar job in juices, margarine, stuff like that. Stops mold and bacteria. And then there's the famous one, MSG, monosodium glutamate. That's a carboxylate salt used purely for flavor enhancement, that umami taste.
Right, MSG. Okay, useful for food, but inside us, in our bodies.
Oh, absolutely critical. Carboxylic acids are central to metabolism. Think about glycolysis. That's the first step in breaking down glucose, sugar for energy. Glucose gets converted into pyruvic acid, or actually in the body, it's the pyruvate ion.
Pyruvate. I've
Yeah.
heard of that. Lactic acid.
Exactly.
Yeah.
When you exercise really hard and your muscles aren't getting quite enough oxygen, that pyruvate gets converted to lactic acid or lactate. That's what makes your muscles burn and feel fatigued
Wow. So that feeling is directly linked to these acids.
directly, and it goes deeper. The citric acid cycle, or Krebs cycle, that's like the main energy factory in our cells.
Okay.
It uses various tricarboxylic acids like citric acid itself, alpha-ketoglutarate acid, succinic acid. They get systematically broken down, oxidized, decarboxylated,
Yeah.
basically dismantled to release energy. And remember, in the body's watery environment, they're all existing as their carboxylate ion forms. They're absolutely fundamental to life.
That's incredible. Such basic structures, such vital roles. Okay, let's shift gears from sour tastes and energy cycles to something maybe a bit nicer. Scents and flavors, esters.
Esters, yes.
Yeah.
These are the molecules often behind the lovely smells and tastes of fruits. Think bananas, strawberries, oranges, often an ester contributing to that characteristic aroma.
How are they made?
Through a reaction called esterification. You take a carboxylic acid, react it with an alcohol, usually need a bit of acid catalyst and maybe some heat. And interestingly, a molecule of water gets eliminated in the process.
Water leaves, the ester forms. Cool. How do we name them? If banana smell is an ester, what's it called?
Good question. It's a two-part name. The first part comes from the alcohol used. It's the alkyl group name. The second part comes from the carboxylic acid. You change the acid ending to oat. So the banana smell, that's largely pentyl ethanoate.
Pentyl from the alcohol, ethanoate from the acid. Got it.
Exactly. Pear flavor, propyl ethanoate, oranges, octyl ethanoate, pineapple, ethyl butanedione, apricots, pentyl butanoate. Lots of fruity examples.
And we can smell them because they're often volatile. They evaporate easily. Okay, but what about health? I think I read aspirin is an ester.
Yes, this is a fantastic story. It really shows the power of chemistry. People knew for ages that chewing willow bark helped with pain. Scientists found the active compound, salicin, which the body turns into salicylic acid. Problem was, salicylic acid is pretty harsh on the stomach.
Ouch.
So back in 1899, chemists at Bayer figured out how to react salicylic acid with acetic acid to make an ester called acetylsalicylic acid. That's aspirin. Making it an ester made it much less irritating.
Wow. So just tweaking the molecule made it usable.
Exactly. And that same molecule, aspirin, isn't just for pain, it's an analgesic. It also reduces fever, antipyretic, and inflammation, anti-inflammatory. And now we know low doses help prevent heart attacks and strokes by stopping blood clots. It's amazing.
It really is. One small change, huge impact. Any other important esters?
Well, there's methyl salicylate, that's oil of wintergreen, very strong minty smell. It's used in muscle rubs because it can actually soak through the skin.
Ah, like in those sports greens.
Yeah, and esters aren't just small, smelly molecules. They can link up to make huge polymers, plastics.
Plastics, like water bottles.
Yep, take terephthalic acid, it's a dicarboxylic acid reacted with ethylene glycol and alcohol with two OH groups. You form long chains, a polyester called dacron.
Dacron, used in clothes.
Clothes, carpets, yeah. But also, amazingly, artificial blood vessels and even heart valves, because it's biologically inert, the body doesn't attack it. And peat, plastic, polyethylene terephthalate. That's the stuff most fizzy drink bottles are made of. Also a polyester. Hugely important material and widely recycled.
From smells to medical implants to recycling, esters are everywhere. What about breaking them down? Can you reverse the process?
You can. It's called hydrolysis, literally splitting with water. It's the reverse of esterification.
Okay.
If you do with acid hydrolysis, you add water, usually with a strong acid catalyst, and the ester splits back into the original carboxylic acid and alcohol. That's why sometimes old aspirin smells vinegary. But ester is breaking down into salicylic acid and acetic acid.
Mystery solved. What if you use a base instead of acid?
That's base hydrolysis or saponification. Reacting an ester with a strong base, like sodium hydroxide, instead of the carboxylic acid, you get the carboxylate salt plus the alcohol.
Saponification sounds like soap.
Exactly. That's literally how soap used to be made, by boiling fats and oils, which are natural esters with a strong base like lye.
Makes perfect sense. Wow, esters are really versatile.
Okay.
Group number 3, amines. What's their story?
Amines. Okay, these are crucial. They're organic compounds that contain nitrogen, basically derived from ammonia and H3.
Futrogen. That sounds biologically.
Hugely important. Amines are fundamental parts of amino acids, which, link up to make proteins. They're also nucleic acids, DNA and RNA. So yeah, literally the building blocks of life.
Wow. Okay. Building blocks. What else?
They also have really significant physiological activity. Lots of medicines are amines or derived from them, decongestants, anesthetics, sedatives. Think about neurotransmitters like dopamine or hormones like adrenaline. Those are amines. And then you have alkaloids. These are naturally occurring amines found in plants, often with really powerful effects. Caffeine, nicotine, morphine, quinine, all alkaloids.
Okay, a really diverse group. How are they classified?
It depends on how many carbon groups are attached directly to the nitrogen atom. If it's one carbon group, it's a primary amine, 1 degrees. Two carbon groups, secondary, 2 degrees. Three carbon groups, tertiary, 3 degrees.
Okay, primary, secondary, tertiary, makes sense. And naming.
Common names often just list the alkyl groups attached to the nitrogen alphabetically, then add ethamine. So CH3NH2 is methylamine. CH3-2NH is dimethylamine.
Got it. What about their properties? Do they dissolve in water?
The smaller ones do, yeah, up to about 6 carbons. Like alcohols and carboxylic acids, that nitrogen atom, especially if it has hydrogens attached, can form hydrogen bonds with water. So good solubility for the smaller ones.
And chemically, are they acids or bases?
Ah, good question. They act as weak bases. Remember, ammonia is a weak base. Amines are similar. They're Brunstad-Lowry bases. That lone pair of electrons on the nitrogen atom can accept a proton, a hydrogen ion, from water.
So they accept H plus add.
Right. They react with water slightly to form an alkylomium ion, like RNH3+, and hydroxide ions, OH. That production of hydroxide ions is what makes the solution basic.
Okay, bases. You mentioned fish and lemon juice earlier. Connect the dots for me.
Perfect example. That characteristic fishy smell. It comes from volatile amines, especially in saltwater fish, as they start to decompose.
Right. Unpleasant.
Very. But what happens when you squeeze lemon juice, which is acidic, citric acid, onto the fish? The acid reacts with the basic amines. It neutralizes them.
Neutralizes them, forming salts again.
Exactly. It forms ammonium salts. And here's the clever part. These ammonium salts are ionic, they're solids at room temp, they're odorless, and they're much more soluble in water than the original amines. So the smell disappears.
That's brilliant. And is that why drugs are often given as salts, like hydrochloride salts?
Precisely. Think about Sudafed. That's pseudoephedrine hydrochloride, or Benadryl diphenhydramine hydrochloride. Making the amine drug into an ammonium salt makes it a solid, stable, odorless powder that dissolves easily in water or body fluids. Much better for formulation and delivery.
Makes total sense.
And this salt versus free amine form has some really serious implications too. Consider cocaine.
Oh.
Street cocaine is usually cocaine hydrochloride, the salt. It's typically snorted or injected. But crack cocaine is the free amine, the free base. You get it by treating the salt with the base.
And what's the difference in effect?
The free base is much more volatile. When it's smoked, it gets absorbed into the bloodstream via the lungs incredibly quickly, much faster than snorting the salt. This leads to a much more intense rapid high, which makes it significantly more addictive.
Yeah.
A stark difference based on that salt versus free base chemistry.
Wow. So it really highlights how much the chemical form matters. What about the amines working inside our bodies naturally? Messengers, you said?
Yes, biogenic amines. They act as hormones, neurotransmitters, vital messengers. Histamine is a big one involved in allergic reactions and inflammation. Antihistamines, like Benadryl, work by blocking histamine receptors.
Okay.
Then you have epinephrine, or adrenaline, and norepinephrine, noradrenaline, the fight-or-flight hormones that get your heart pumping, increase blood sugar, get you ready for action.
Adrenaline rush, right?
That's them. And dopamine, crucial for movement control, mood, reward pathways. Lack of dopamine is linked to Parkinson's disease. Serotonin is another key one, affecting mood, sleep, appetite.
So many critical roles. What about amphetamines? They sound similar.
They are structurally similar to epinephrine. Amphetamines are synthetic stimulants. They rev up the central nervous system, increase heart rate, blood pressure, reduce appetite. Some are used medically, like Adderall for ADHD or Benzedrine as decongestant sometimes. But others, like methadone or speed, are highly abused and very addictive.
Right. A fine line between therapeutic use and abuse.
Definitely. And those plant alkaloids we mentioned earlier, many are amines with powerful effects. Caffeine is a stimulant. Nicotine is highly addictive. Quinine treats malaria. Atropine is used medically too. Then you have the really potent painkillers from the opium poppy morphine, codeine, and their derivatives like heroin and OxyContin, which are tragically central to the opioid crisis. Amines are powerful molecules.
Incredibly powerful for good and ill. Okay, last group. Amides. How do they fit in?
Amides. Think of them as cousins of carboxylic acids. You form them by replacing the HOH group of a carboxylic acid with a nitrogen atom, which might have hydrogens or alkyl groups attached.
So instead of C double bond O single bond OH, it's C double bond O single bond N.
Exactly. The reaction to make them is called amidation. A carboxylic acid reacts with ammonia, NH3, or primary or secondary amine. Again, like esterification, a molecule of water is eliminated.
Water leaves again. How are they named?
You take the name of the carboxylic acid, drop the oic acid or indic acid ending, and add ethanamide. So ethanoic acid gives ethanamide. If there are alkyl groups on the nitrogen, you use N or NN to show they're attached to the nitrogen, like N-methylanamide.
N for nitrogen. Got it. Properties, are they bases like amines?
Crucial difference. No. Amides are generally not basic. That lone pair on the nitrogen is less available because of the adjacent carbonyl group. But like the others, smaller amides, up to maybe 5 carbons, can hydrogen bond with water, so they tend to be water soluble.
Okay, not basic, but can be water soluble. Where do we find amides?
Health and medicine.
Big time. Urea is a really important natural amide. It's the main way our bodies get rid of excess nitrogen from breaking down proteins. Kidneys filter it out into urine.
Urate.
If your kidneys fail, urea builds up in the blood. That's a toxic condition called uremia. On a different note, urea is also mass-produced as fertilizer.
Wow, waste product and fertilizer. Yep. Then there are barbiturates. These are cyclic amides, phenobarbital, pentobarbital. They act as sedatives, sleep aids, powerful drugs, but also habit-forming.
Sedatives, okay.
Any others?
Yes, common pain and fever reducers. Many aspirin substitutes are amides. Acetaminophen, the active ingredient in Tylenol, is an amide. It works well for pain and fever, though it doesn't have as strong an anti-inflammatory effect as aspirin. Phenacetin was another one, though it's less used now due to side effects.
Tylenol, so that's an amide. Interesting. And can amides be broken down, like esters, hydrolysis?
They can, yes. Amide hydrolysis also involves splitting the molecule with water, breaking that carbon-nitrogen bond. It usually requires stronger conditions than ester hydrolysis, like strong acid or base and heat.
And what do you get?
With acid hydrolysis, you get back the original carboxylic acid and an ammonium salt, since the amine formed is basic and reacts with the acid catalyst. With base hydrolysis, you get the carboxylate salt and the free amine or ammonia. These reactions are fundamental to how proteins are broken down in digestion, for example. Right, breaking down those peptide bonds, which are amide links.
Precisely. Peptide bonds are amide linkages.
Okay, wow. So we've covered quite a bit. Carboxylic acids, esters, amines, and amides. It really feels like these structures are just everywhere.
They absolutely are. From the tang of a lemon to the smell of a flower, the medicine that eases your headache, the plastic bottle you drink from, the proteins that make you you, and even, as we saw with Lance, keeping our environment safe. It all comes back to these functional groups.
Understanding these building blocks really does open up a new way of seeing the world, doesn't it? Makes you appreciate the chemistry behind everyday life.
It really does. You start seeing the connections.
So next time you taste something fruity or take a Tylenol or even just, I don't know, smell rain on pavement, which can kick up soil amines, maybe pause and think about that intricate dance of organic molecules. It really makes you wonder, doesn't it? How much more is going on at that microscopic level that shapes everything we experience?